Uh, Welcome to fifth lecture, stability of structure. So, let us briefly recapitulate what we were discussing. So, we were discussing symmetric, asymmetric bifurcation with stable or unstable post-critical behavior, and we have demonstrated. So, this behavior that is portrayed by a system in which a rigid bar is restrained by inclined spring. Okay. So, basically the restoring force varies, okay, with the positive theta and negative theta differently, okay, because the lever arm, when you are taking moment, restoring moment, so that will, the magnitude of this will be dependent on the magnitude of theta. For positive theta, that means for clockwise theta, it will be less, for anti-clockwise theta, it will be more. So, depending on the value of theta, it will show stable or unstable, behavior, right. So, a stable fundamental path will bifurcate into a asymmetric, post critical path, right. And so, the rightward, the right path actually which is declining path, right, that will be unstable, and the left side will be stable. So, the bifurcation, the stability diagram we have demonstrated, and on incorporation of imperfections, the equilibrium path for the imperfect system will be asymptotically approaching to the perfect system, and the system shows notorious imperfection sensitivity that we have demonstrated. So, it follows the half power law, right, Quater's imperfection sensitivity. That means, if there is slight imperfection, there is a significant drop in the critical load, right. And then if we look into the energy for the potential energy function, then these are the expressions that I have written. So, theta is basically the degrees of freedom, right, and then alpha is the imperfection. So, what we assume, this is symmetric term, this is asymmetric term, right, this is asymmetric term, and this is also asymmetric term. So, this asymmetric term, right, these basically demonstrate the dependency of the on dependency of the system behavior, the stable and unstable, on theta. Okay. So, for the positive theta is, it will show a stable path, whether for negative theta, for positive theta it will show unstable path, for negative theta it is stable, right, which is also corroborated with the slope of the equilibrium path as well, right. So, this kind of asymmetric term in the potential energy expression you will not see in the asymmetric, in the symmetric bifurcation, whether it irrespective of whether it is stable or unstable post critical behavior. Okay. There it was only quadratic term or quartic term or sixth or eighth term, okay, if you take higher order, but here it is cubed first order term, right, and then cubic term, okay, which depends on theta, right. That is what I wanted to point out. Okay. Now, I will just, before jumping into next, so all three behavior we have covered. Okay. The first behavior was symmetric bifurcation, but stable post critical behavior, right, and imperfection insensitive. The second is symmetric bifurcation, right, but with unstable post critical behavior, and this is mildly imperfection sensitive. The third one is asymmetric post critical behavior with stable unstable both type of post critical behavior, and it is notoriously imperfection sensitive, right. Now, fourth system we are going to consider, okay, but before that, for these three system we are going to see the topology of the potential energy function. Okay. So, for the first kind of system I am just plotting pi, okay, here the potential energy function pi, okay, and as a function of theta, right, and this is for different p. So, for the stable bifurcation it will look like this. So, for different I am increasing the value of p, okay. So, this is for p1 maybe, this is for p2, this is for p3, P3 means P critical 1 rather, okay, and after that I am going to draw, So what we see, this is for the first kind of system where it is symmetric bifurcation, stable post critical behavior. You see that, potential energy function is a concave surface, right? Then as soon as P1, P2, these P1, P2 are less than P critical. Okay, as soon as critical value is reached, then the stable, configuration is different. Theta is equal to 0 is not a stable configuration, right? This corresponds to stable configuration in the fundamental path, right? But then you see here it is convex, here it is unstable, right? So at theta is equal to 0, it is no more stable, okay? And then with increasing value, so increasing value of critical, P critical 2 means, slightly higher value, then this, potential well will be little expanded and things like that. Clear? So this is the for the first kind of system, okay? Then second kind of system, it looks like this. You see that for the symmetric bifurcation but unstable post critical behavior, you see that fundamental path is stable here, right? This concave surface, after that these are unstable, right? And then slightly higher load, okay? These are all, smooth, please note that, okay? Still, slightly higher P2, but still this P2 is less than P critical. It may be this, potential will expand, okay, but still it remains same. As soon as it is reaching critical value, then you see, then this this become unstable, but here, here still it remains like this, okay. But as it is much higher than critical, you see what happened. You see that these are unstable. You see that this become convex, okay. That means post critical path is unstable. Understand? This is for the symmetric but unstable post critical behavior, right? Now for the third thing, which we have discussed just now, how it will look like. Let me say so that thing to you. Here, so here you see that here, once again, do you see that in previous two cases, that's where potential energy function is symmetric with respect to fundamental configuration, theta is equal to 0, right? These are all symmetric, right? Here it is asymmetric. You see that here it is stable when P is less than P1 is less than P critical, right? But here it is unstable. Do you see that? That's what I say. Right one for theta anti-clockwise it was stable, but theta clockwise is unstable, right? Then slightly above, slightly higher, but still it is this potential will expand a little bit, but still it is unstable. As soon as reaching P critical, then it is not unstable. This is also unstable, right? And this is kind of flat. So that okay. Then what happened? P greater than P critical. That means left hand side, left hand side it is stable, but right hand side unstable. You see that? Here this is stable because it is concave, but here it is unstable. That's what I said. The right hand side is unstable, left hand side it is stable. Clear? So this is due to asymmetry. Clear? So, do you understand the topology of the potential energy functional, right? And in all these cases, these were all consisting of in potential energy function, the term will be either in square or fourth power or sixth power, eighth power, more and more term we include, right, by expanding the potential, trigonometric function. Okay, but this case it will include the first term, okay, which distinguishes between theta positive or negative, cubic term, fifth order term, seventh order term, and so on here. And whenever these odd terms will be there, then it will be show this notorious imperfection sensitivity. All these cases is half power sensitive. These two cases, this is insensitive, it is two-third power sensitive, right? Clear? Okay. So now we are going to consider the last type of. So, let us emphasize the third kind of system where this asymmetric bifurcation, okay, unstable. This is kind of, and then imperfection sensitivity. This kind of behavior is portrayed by asymmetric buckling mode in cell, okay. Both the cylindrical cell as well as spherical cell, under pressure, cylindrical cell under axial compression and spherical cell under pressure, uniform pressure, they will show both symmetric as well as asymmetric buckling mode, okay. And this asymmetric buckling mode will show this kind of behavior, okay. That's why. So now we are going to consider, all the previous example, we have seen that the transition from stable to unstable was adjacent, meaning the gradual transition you can see, okay. So there was, for the perfect system, the system was bifurcating into, so from the fundamental part to the a secondary path or post critical path, right, that bifurcation. So it was adjacent, stable to unstable, transition was adjacent, okay, to alternate equilibrium configuration, right. But now we are going to consider a system, and that is the last system, we are encompassing essentially all the type of behavior that is portrayed by elastic system, elastic structural system. So now we are going to consider a system classes of system in which, and we are trying to demonstrate using very simple example, namely that is called von Mises truss, okay, which is simply supported, and then it is basically two members are having axial stiffness A by L, okay, and then subjected to concentrated load P, on the top, and these are length L. Initial inclination was theta 0, and then after perturbation, that is taking a configuration theta, which is defined by theta, okay, intermediate configuration. So it is a system in which stable to unstable transitions are not adjacent. Okay. So, the equilibrium configuration for stable to another stable equilibrium configuration is far apart. I will show you how it is possible. Okay. So, now for this kind of system, you please find out. So, the first lesson in any stability analysis, you have to perturb the system. Initial count theta 0. So, theta, what is the potential energy function of pi strain energy minus work done, right? What is the strain energy? Strain energy will be consistent half. There are 2 k into delta square and minus p into capital delta. So, k is the stiffness of individual this string. Stiffness is nothing but A by L. A is the area, E is the modulus elasticity length. Of course, it will not be L, but if this is L, then it will be L, sec theta or whatever, right? Something like that, maybe L dot I am saying, okay. But I am assuming this is K, right? So, delta square minus P into delta, this capital delta is nothing but this one, right? And this delta, let us find out, okay. This delta will be nothing but this, huh? So, this delta will be what? This delta will be what? Initially this L sec theta 0, L sec theta 0 minus L sec theta, right. So, L sec theta 0 minus sec theta, and capital delta is L tan theta 0 minus tan theta, right. So, let us see k delta square, k delta square means L square, sec theta 0 minus sec theta square minus P L tan theta 0 minus tan theta. So, now we will see equilibrium configuration del pi del theta is equal to 0 for equilibrium path, right. So, equilibrium, let us differentiate. So, k L square 2 sec theta 0 minus sec theta, and then this is minus sec theta tan theta, minus PL, and this is minus sec square theta is equal to 0, and then if you see, minus 2 k L square well, I mean, you can write it like this. You can take this side. So, PL sec square theta is nothing but, take that side. So, 2 k L square sec theta tan theta sec theta 0 minus sec theta, okay. Or from here, if I further simplify it, please go that side. So, sec theta will just cancel out, this will go sec theta, and then PL. So, sec theta means 1 by cos theta, sin theta by cos theta. So, cos will cancel out. So, PL will be nothing but 2 KL square, sin theta, and then sec theta 0 minus sec theta. And if we just take this out, it will. So, this is basically giving the equilibrium path. So, now I am removing this part, and I will come back further. So, here it will look like something like this, So, is 2 KL sin. So, you can see that, at theta is equal to 0, p is equal to 0, right, and that at theta is equal to 0, p is equal to 0, and at theta is equal to plus minus theta 0, p is 0, right, fine. But at some p, and then if you plot it, it will look something like this. So, you see that theta is equal to 0. So, this is p and this is theta. This is basically theta is equal to minus theta 0, and this is theta is equal to theta 0, and this one where this takes value, this theta is equal to minus theta c, and this is theta is equal to theta c. I will just explain to you that why it is dotted. The solid line represent the stable path, whether the dotted line represent the unstable path. But this plot is for the equilibrium path. Okay, this is the whole equilibrium path. Okay, now if you go further, it will continue. It is not that it will not continue. It will continue. Okay, it will continue. Okay, something like this. It will continue. Okay. So now, at what value it is being maximum? For maximum p, peak maximum p, dp d theta is equal to 0. So, how it is dp d theta is coming, you just differentiate it. So, cos theta sec theta 0 minus theta plus sin theta minus sec theta, and sec theta is sec theta tan theta. So, sec square theta tan theta is equal to 0. Okay. So, then you simplify that, and if you simplify, so what you will get is this is cos theta sec theta 0 minus cos theta sec theta is 1, right, plus minus sin theta cos theta, so minus sin theta 1 by cos square theta sin theta phi theta is equal to 0, and this one will be sec theta, then cos theta. I am just writing to be sec theta minus 1 minus sin square theta by cos square theta, and 1 by cos theta is equal to 0. Okay, so here what you are going to get is, simplifying it further. If you simplify it further, then you will see it's going to be sec theta 0 sec minus 1 minus tan square theta, and 1 by cos theta. 1 by cos theta sec theta is equal to 0. Okay, and sec theta 0 minus theta minus tan sec. So it will be, you please check the calculation. It should come, dp d theta. Okay, so it should come as cos cube theta minus, okay, 1 plus tan square theta, sec square theta, so sec theta minus tan square theta means please check the calculation. I think I missed, this must be sec square theta. So 1 plus tan square theta will be 1. Okay. 1 plus sec square theta is equal to 1 plus tan square theta. Okay. So ultimately, what you are going to get is an expression where, so cos theta into sec theta 0 minus sec square theta, okay, is equal to 0, something like this you will get, okay. So if you or I mean final expression will come dp d theta, dp d theta will come as 2kl square from there, okay, by cos 2kl square 2kl square. Please note that cosine of theta minus into cos square of theta, and then you will get cosine cube theta minus cos theta 0, okay. This is the expression you will get. So now, so dp, this will be the final expression, okay. So if you whatever I was trying to derive, you please check it. Ultimately, you will get this expression, okay, if you differentiate this, okay. Now, dp d theta is equal to 0. That's what for maximum. So that means cos square theta minus cos theta 0 must be equal to 0. So this equation need to be solved, and then for this by solving theta is equal to theta c. Where theta is equal to theta c, dp d theta is 0. That means these two point, where p is maximum, I am indicating as theta is equal to theta c, and then there will be two root, okay. One will be theta is equal to theta c, because cos of minus theta is cos theta, right. So at theta is equal to theta c, maximum value of p is occurring, okay. So that's what from where we are going to get that thing, by solving this equation cos cube theta minus cos theta 0. Theta 0 is known. So from here, theta is nothing but 1/3 cos theta 0 1/3, and that's okay. Okay. So theta c we have obtained. Now you may still recall that dp d theta is nothing but d2 pi d theta 2, right? Here it will be same expression, but only there is a change in sign, okay. That's what I will just, so please note it down, dp d theta, okay. And if you try to find out del 2 pi d theta 2, so del 2 pi d theta 2, I am just writing the expression just to save time, del 2 pi d theta 2. So this one will be from there, okay, whatever the expression was pi was, so it will be 2kl square sec square theta plus 2 tan square theta. It's a little long expression, but minus sec theta 0 sec theta sec square theta plus tan square theta plus 2pl sec square theta tan theta, okay. Now what is p for the equilibrium path? What was p? P was this. So if you substituting p in d2 pi d theta 2, substituting p equilibrium, substituting, the way we find out the substituting p, you will get, and then if you simplify, you will get del 2 pi d theta 2 as 2KL square by, that will be a relatively simpler expression, but you have to do quite a lot a manipulation. Okay, please note that ultimately you will get this expression cos cube theta. So please note that this is the expression for, so what we did, the potential energy function we differentiate once, then second time we have differentiated, and then we have substituted equilibrium path into that. So d2 pi d theta 2 in terms of theta 0 and this expression. Now what is dp d theta? This expression. Do you see the difference? The difference is this expression is same in both the way. Here also this is always positive, cos to the power 4 theta is always positive, here also is positive. Only thing is that this is exactly negative of that. So that means unlike all previous cases, here dp d theta is nothing but minus d2 pi d theta 2. Do you see that? This is very important. Okay. So what do you see here, that unlike all previous cases, but in all these cases, here they are qualitatively same except the difference in sign. This is nothing but minus dp d theta. In both the cases, they are nothing but tangent stiffness, right? So now I will explain to you why this thing is happening. So when it will be stable, when this expression is greater than 0, d2 pi d theta 2 greater than 0 is stable. So when it will be stable, when it is 0, at theta is equal to, if this equation you have solved to obtain what, dp d theta is equal to 0, that means maximum p, for maximum p what, theta is equal to theta c, right? Now if theta is greater than theta c, this is positive. When it is positive, you see that. So please note from these two, so we know that d2 pi d theta 2 is dp d theta. Fine, I am removing this now. And what I would like to concentrate you is on the fact that, please note that, look, so at theta is equal to plus minus theta c, what we have seen that dp d theta was 0, and so is d2 pi d theta 2, and because that basically implies cos theta 0 was nothing but cos cube theta c. That's what theta c you have obtained. Theta 0 is known, theta c. So now if this is 0, this is greater than 0, if and only if mod of theta greater than theta c, if mod of theta greater than theta c, this is positive, right? Mod of theta greater than theta c means what? Mod of theta greater than theta c, meaning theta is greater than theta c, less than theta minus theta c. Okay, theta must be greater than theta c and it must be less than theta c. That means delta theta c is this. So this is nothing but stability boundary. When theta, so which one is stable? This one is stable. This one is stable. That's what I have explained to you. This is, that's why it is, I have drawn, this is solid line is stable. This is stable. And in between this, between theta is equal to minus theta c and this. So between theta, if theta is greater than minus theta c, less than theta c, it is unstable. This is unstable boundary. This is unstable. Unstable. This is unstable. This is stable. This is stable. This is stable. Please note that. So from here to here, this is unstable. This is unstable. Here it is stable. Beyond this it is stable. Beyond this it is unstable. This is stable. That's what this is solid line. This is now. So you see that. Now what will happen? I will explain to you. You have taken theta, some value greater than, please be very careful. Some theta, where theta is greater than theta 0. Okay. So what I am going to do, I am doing an experiment, a load control. I am gradually increasing the load, I am following this path, increasing the load, right? Then I am coming theta is equal to theta c. That means I am just increasing the load, I am, right? Theta is equal to theta c. If I am coming here through load control, you know what is load control and what is displacement control. All of you are doing experimental method, right? If I am doing load control and gradually increasing the load, decreasing the theta and increasing the load, I am reaching theta c. Then if I go by load control, what will happen? This will not follow that path, this will suddenly jump here through load control. This fellow suddenly from point maybe A, it will come to point B. If I am going by load control, load control, right? What is going to happen then? This fellow suddenly will jump here and it will come theta is equal to minus theta 0. That means from here it will suddenly snap through theta is equal to, so this will completely come down and it will be something like that, right? Theta is equal to minus theta 0. Because this is stable. Why it is not possible to follow this path by load control? Because this is an unstable path. Through load control you cannot follow. Through load control you cannot follow an unstable path. So it will directly jump to a stable configuration. So this was a stable configuration, from there it will come to a stable configuration. But what is happening? So a stable configuration to adjacent stable configuration are not adjacent. They are a finite distance apart. Do you see the difference between bifurcation instability and this instability? This kind of instability is called snap through instability. This is called snap through instability. What is happening is snaps through instability. Now, here when you are now we are decreasing the load. That means here when it is coming down, here the load is there. Load is still vertical. Now you are decreasing the load. From here I am decreasing the load, decreasing. And I am going to negative. Negative P means I am changing its what? The sun. From downward it is upward. I am pushing it. I am coming here. Load control. Then if I further push it, it will not follow this. It will suddenly from here it will suddenly jump there. Once again another snap through. That means when I am pushing it, it will suddenly jump, go down, go upward, and it will suddenly reach there. So from AB, I am writing C and I am writing it D. So from C, it will suddenly snap through configuration D. From one stable configuration to another stable configuration. Once again, the stable to stable jump is not adjacent. It is finite distance apart, right? Now, does that means that it will never be able to follow this path? Of course, it will be able to follow this path. How? If you make the experiment displacement control, instead of load control, if you allow it to be displacement control, then this path can be traversed, right? So this can only be traversed through a displacement control. Okay, control. Do you understand that? Another thing, that see why dp d theta is negative sign than that of d2 by dt2. You see that here the slope is positive, but it is unstable. That means dp d theta, that's why it is dp d theta was negative of d2 by d theta, right? Because it's a positive slope, still it is unstable. Positive slope generally implies what? It is stable, right? So what is happening here, that this kind of system, Mrs. Truss, it doesn't lead to bifurcation. It leads to snap through. Of course, in literature, you will see a conflicting little statement that, there are, I have seen that people are referring snap through as also bifurcation. Only thing is that the bifurcation is occurring from one stable configuration to another stable configuration, but it is not a distance apart. It is not adjacent, okay? Non-adjacent, okay? So, another thing what you please see that for when it is going from A to B, this transition, we are doing a static analysis. In none of the cases we are doing a dynamic analysis. Inertia we have not considered, static analysis. We are just simply minimizing the potential energy, right? But do you think from when it is the system is going from A to B, will it happen statically? It will not happen statically, it will always happen dynamically. From here, when it will jump there, it will happen momentarily. That means there will be significant inertial force and there will be kinetic energy and it will oscillate. Okay. And eventually, if there is no damping, it will perpetually oscillate, but there is damping, so eventually it will come down to rest. So the kinetic energy will be dissipated in form of heat. And what is the amount of energy? The amount of energy is nothing but this area of the loop. See, from here you are jumping there and then you are coming once again jumping. So this area of the loop is the energy that is being dissipated through this snap through behavior. When it is going from here to here, it is this area of the loop. When it is coming from here to here, it is, if you are taking the whole loop, then these two. So you see that a purely elastic system, but this system is showing hysteresis. Where did you see hysteresis? In earthquake engineering structural dynamics, when the system is material nonlinear, meaning when the system is yielding. So you see that, when did you see in dynamic structural dynamics, a concrete structure, steel structure is going, and then it is yielding, it is coming back and it is going, once again it is going, coming, and cyclic loading, unloading happening, right? So this is the hysteresis that you have seen, but this hysteresis was what? Due to elastoplastic hysteresis. In your structural, any reinforced concrete column, of course that hysteresis will be a little more complicated, or steel structure when it is going, right? But here it's a purely, this is called elastoplastic hysteresis, right? Load displacement, here it is load, here it is displacement, right? But here this is a purely elastic system, yet the system is showing so purely elastic system portray in hysteresis, which is little uncommon. Okay, elastoplastic system can show hysteresis. It's a geometrically nonlinear system. Okay, here, and it is showing hysteresis. So what here we should comment, I am just writing, but please note that here there is no bifurcation, though stable to unstable transition is, it's a finite distance apart and it happens momentarily. And please note that this system imperfection doesn't have much role to play. That's what we are not studying imperfection sensitivity. The system which demonstrates snap through or hysteresis, okay, doesn't have much influence of imperfections. So that's what we don't care about imperfections. But another very important stuff is that unlike all previous system, there is another important thing. This system is influenced from the very beginning by geometric nonlinearity, and that's what is showing this kind of behavior. Okay, so this is called a Mises truss. Okay, now I will show you. See, this system we never approximated sine or tangent term or second term, whatever has appeared in the potential energy function or load displaced equilibrium path, we never linearize it. Do you see that? In all previous cases, we were basically, preferably we were linearizing, we were expanding it using, Maclaurin series expansion of sine, cosine. So a trigonometric expression, we preferred to express it in terms of, a polynomial. Because potential energy function, when expressed in terms of polynomial, will reveal important clue about the instability behavior. Both the stability, stable path, unstable path, and then particularly imperfection sensitivity and nature of bifurcation, whether it is symmetric bifurcation, whether it is asymmetric bifurcation. Okay. Please note that earlier we were talking about symmetric bifurcation, asymmetric bifurcation. An equilibrium path were either symmetric or asymmetric. Here, equilibrium path is what? Antisymmetric. Here exactly this is mirror opposite. So equilibrium path is antisymmetric. It is neither symmetric nor asymmetric. It is antisymmetric. Imperfection doesn't have much role to play. And another important thing, the system will portray the system has significant pre-critical non-linearity. And I will show you what is the consequence of pre-critical nonlinearity, because see, pre-critical nonlinearity, why it is important. Please note that in all other cases, we have seen that when we are expanding it in terms of potential energy functional, and then we have linearizing by dropping the higher order term, polynomial term. Okay, we are linearizing the system, and that was leading to what? The finding out critical load was leading to what kind of problem? Eigenvalue problem. Initially, it was a trigonometric eigenvalue problem, because del pi del theta is equal to 0. So, everything was expressed in terms of trigonometric function for this simple system, but ultimately we are expanding in terms of polynomial. That is what it was, and neglecting higher order term, it was converted into a algebraic eigenvalue problem, and by solving that eigenvalue problem, you are obtaining the critical load as well as the buckling and the respective mode shapes, and those mode shapes were serving as a legitimate basis to further simplify the potential energy function, where there will be no cross term, or all terms will be uncoupled, right? That is what I have also demonstrated, right? That also helps you in tracking down the topology of the potential energy function, and by looking into just those coefficients, you can comment on the stability, right? But here what will happen? Here you will see, if we arbitrarily go on linearizing, it will be very much misleading. That is what I am going to show it now. What will happen if you linearize it? So, system which display snap through, you cannot linearize it arbitrarily. You cannot just express this in terms of polynomial functions, and then if you analyze based on this kind of simplification, it will be very, very misleading. That is what I am going to show it now. Another thing that I would like to point out, so equilibrium path you are getting P as 2KL sin theta sec theta 0 minus sec theta, okay, and we are finding out dp d theta. Dp d theta was expressed as, okay, dp d theta, and from dp d theta that was making 0, that was giving you the equation that cos cube theta must be equal to cos theta 0 or sec theta. So, from there, by solving, you are getting theta is equal to theta c, okay. Now, P basically, okay, so if you substituted this, okay, substituted into there, okay, by combining, okay, if you combine in this, then the P is equal to 2KL sin theta and cos theta sec theta, so sec cube theta minus sec theta, so 2KL sin theta and sec theta you just take out, sec square theta minus 1, so 2KL tan theta or tan theta, and this one is also tan theta. So, tan theta, no, tan square theta. So, 2KL tan cube theta. So, 2KL tan cube theta, this basically is also, if you just draw it here, that will show you, so tan cube theta, okay. So, here please show, I am just drawing it tan cube theta, okay. So, this is basically stable unstable transition, okay, please note that. Huh? You know how tangent look like, it's cubic round tangent. So, this is nothing but P is equal to 2KL tan cube theta. So, 2KL tan cube theta is this. So, this basically represents, you see that this is giving you stable unstable boundary, okay. Huh? So, I am just superimposing that thing to you, huh? Please note that. Huh? So, this is nothing but, this is the stable unstable boundary, huh? Stable unstable So, essentially what happened that dp d theta from where whatever expression you are getting, if you just substitute it over there now, then the equilibrium path becomes simplified, okay, and that is what I am just drawing this one, and that basically it will be intersecting these two peak curve, right. So, in one way you can say that, okay. Now, what I will do, did you note it down, all of you? I will just show you what will happen if we linearize it, okay. So, the potential energy function, if you please recall, the expression for the potential energy functional, okay. The potential energy functional was k L square sec theta 0 minus sec theta square minus P L tan theta 0 minus tan theta. That was the expression for P phi, right, potential energy function. Now, what I am going to do? So, I am going to, I am trying to linearize it, meaning I am trying to approximate this trigonometric function in terms of its expansion, okay. And let us see what happens. This will teach us a great lesson. 1 plus theta 0 square by 2 minus 1 minus theta square by 2 square P L theta 0 plus theta 0 cube by 3 minus theta cube upon 3. Please note that for the sake the I am neglecting the quartic term, only quadratic term, okay. Please note that. So, it is approximate, it is not exactly equal, and for the tangent function I am only including the cubic term, okay. So, then when I am including, so I will just simplify it further, k L square by 4 theta 0 square minus theta square minus P L, okay, theta 0 minus theta 0 minus theta plus theta 0 cube minus theta cube 3, okay. Then, so do you see that how we are how we are expressing in terms of polynomial, and we are neglecting higher order terms, okay. We will see what will happen by linearizing, okay, but that is the first stepping stone to linearization, okay. Okay, then d pi by d theta, d pi by d theta will be what is equal to 0, d pi by d theta will be nothing but k L, I am writing the simplified expression, okay, k L square theta square theta square minus theta 0 square plus P L 1 plus theta square must be equal to 0, and this will give the equilibrium path. So, P equilibrium path is nothing but k L theta 0 square minus theta square, okay. So, do you say that we have obtained the equilibrium path from the minimization of potential energy, and this is the equilibrium path, P is equal to k L theta, this one. Let us see what we will lose, okay. Now, we will do second order differentiation. So, if you differentiate it further, then you will see it will k L square 3 theta square minus theta 0 square plus P L 2 theta is equal to 0, and from there you will see that of course d2 pi d theta to 0 is equal will give you P critical, right. So, here you will get P critical is nothing but k L by 2 theta theta 0 square minus 3 theta square, okay. So, I am just removing the upper part, okay. I am just keeping these two, all of you have noted down this, okay. What we see that P critical is KL by 2 theta and theta 0 square minus 3 theta square, and P equilibrium path is K L theta 0 square what do we understand that the equilibrium path when this p is equal to 0. So, from there what we can, theta is equal to plus minus theta 0, p is equal to 0. Is that correct? Yes, that is correct. Theta is equal to 0, theta is equal to minus theta 0, p is 0. That is fine, right? Even at p theta is equal to 0, it is also 0, and at theta is equal to 0. That is correct. That is okay. So, through linearization we are getting that information correct. What about p critical? That implies the stability boundary. So, the stability boundary, theta 0 square become 3 theta square and theta become plus minus theta 0 by root 2. Okay. So, basically mod of theta 0. That means, what does it mean? That means theta, greater than, theta 0 by root 2 less than minus theta 0 root 3, it is stable. Is it correct? No. Theta is equal to theta c does not correspond to theta 0 by root 3, right? Theta c, so not theta 0 by root 3, right? Theta c you obtained by solving the trigonometric function, right? Sec theta 0 minus sec cos theta 0. This theta c we obtain from solving the equation that cos theta 0 must be equal to cos cube theta c, right? From by solving this equation we obtain this thing. But what the stability boundary is showing that theta greater than theta 0, that means here the stability boundaries are wrongly interpreted, right? The stability boundary, the information about the stability boundary is wrongly given. Nevertheless, it is indicating that they are non-adjacent. The transition from stable to unstable or transition from stable to stable configuration, alternate stable configuration is still non-adjacent, and it is showing the snap through, but their estimate is wrong. Theta 0 by root 3 is not correct through linearization. So, this basically implies that you cannot arbitrarily linearize all the system. A system which shows snap through, a system which demonstrate or display snap through behavior, its behavior cannot be represented through linearization. If you linearize that, it will give you inconsistent result. If you linearize a system which is showing snap through, it will give you non-consistent, it will lead to misleading result. And why that is so? Because this system from the very beginning is have pre-buckling nonlinearity. Of course, pre-buckling nonlinearity is other system also shows, but here the nonlinearity is more significant. That cannot be meaningfully linearized. So, you shouldn't be misguided by the notion that all the system can be linearized, because just because linearization give you a nice eigenvalue problem by solving of which you will get the critical value, but that may be very misleading for many systems, such as the system which demonstrates snap through. In fact, a number of cell buckling, cylindrical cell and then spherical cell under pressure, those show snap through behavior. Okay, even there are other example as well. Okay, so these kind of systems shouldn't be linearized. In fact, this mistake has been made by many by scientists in the past. In fact, when people were basically trying to solve various systems, one such example is that a common example is shallow arch, flat arch, a arch in which the rise is relatively small comparing to the span. You know all about arch, right? You have studied the mechanics of arch, right? But when you study the buckling of arch, buckling or post buckling behavior, if you linearize it, it will not show the snap through, it will not reveal the snap through behavior. The same thing for arches. So, in fact, we have written one of our paper, when we are writing them, the misleading information that even it was published in many literature, in literature, we have referred, their arbitrary and indiscriminate linearization lead to misleading and apparently conflicting result and wrong information, because people did not linearize until that time that this system cannot be meaningfully linearized. Okay, let it be linear and we should solve it that way. Okay, understand that? Okay, so with this we have we essentially covered all the 4 basic system. We call it toy problem, but essentially with these 4 toy system we are able to demonstrate all the physical behavior that we encountered in elastic stability of structure, right. Now we are going to demonstrate one important thing about imperfection sensitivity, that is through modal interaction. Okay. For that we are going to consider a system which is called Augustus column. What we are going to demonstrate? We are going to demonstrate the implication of modal interaction. Modal interaction. What happened in the when you did modal analysis in dynamics, you have seen that system, linear system, you have a nice mode shapes. Similarly, in for buckling also you have nice buckling mode shape, but there are systems in which this buckling mode interact. And why it will interact? Because in presence of nonlinearity. What will happen? So what we are going to demonstrate is that a simple, apparently simple system which has 2 uncoupled mode, nice mode, they will be imperfection insensitive. But as soon as they interact through nonlinearity, that coupled behavior become imperfection sensitive. That is what we are going to demonstrate using a very simple example. So this example we are going to consider is called Augustus column. So this is named after scientist. So this column is really this is you consider like this, maybe this is x, this is y, and this is z. So there is a system, this is a rigid bar, okay, and this rigid bar is is connected to the system with this spring, and this is P, and this is length L. Okay. So we are assuming that maybe with z axis it is. So if we just project it with x, this is maybe P, this is x, and this is z, this is y, and this is z. Assuming this is this angle theta 1, maybe this is angle theta 1, this is angle theta 2, and then the other, so this angle will be 90 degree minus theta, theta 1, and this is 9. So the angle that makes with the z axis, I am assuming this is phi, right. So from the properties of the direction cosines, right, we can write that cos square 90 degree minus theta 1 plus cos square 90 degree minus theta 2 plus cos square phi is equal to 1. Phi is the angle with z axis. So then this is sine square theta 1, this is sine square theta 2 plus cos square right. You understand what I am trying to do, right? This angle is P. So I am assuming this is C1, this is rotational spring. Why we are causing rotational spring? Because we know that a rigid bar restrained by rotational spring, stable bifurcation, so that is imperfection insensitive, right? So what is the potential energy function? Potential energy function is nothing but half, and we are assuming that maybe alpha 1 and alpha 2 are the imperfection, half C1 theta 1 minus alpha 1 square half C2 theta 2 minus alpha 2 square minus P L 1 minus cosine cos. So, you may wonder that why I am not including cos alpha 1 cos alpha 2. Why we are not including? Because if you see here it is appearing in directly alpha 1 alpha 2, right. So, cos it will inherently it will involve 1 minus alpha 1 square by 2. So, square term or quadratic term we are neglecting comparing alpha to alpha. Okay. So, the influence of imperfections in these terms can be neglected. You understand what I am trying to tell you, right? Right? Okay. But from phi I obtain this one, right, from where I am getting this thing, right, because for any point all the directions cosine must follow this rule, right. So, that is what phi can be expressed in terms of theta 1 theta 2. So, essentially this system is Augustus column has 2 degree of freedom. This is a 3D, it is in 3D plane, okay. So, it is inclined at angle phi with the z axis with some angle theta 1 with this one x axis and theta 2 with y axis, right. So, let us before doing that let us simplify this one, okay. So, how will you simplify? So, 1 minus sin square theta 1 minus sin square theta 2. So, 1 minus sin square theta means theta 1 minus 1 cube by factorial 3 means 6, right, square minus theta 2 minus theta 2 cube by x square. So, I will just I do not want to waste time for simplification. So, quickly I will do, okay. So, this one is 1 minus theta 1 square minus theta 2 square plus theta 1 to the power 4 by 3 plus 3, okay. I will just, so theta 1 to the power 6 term, 6th order term we are neglecting, okay. So, that essentially considering theta 1 square plus 2 theta 1 into theta 1 gives 6, so 4th order terms, okay. Other terms we are neglecting, clear, okay. So, then from here what we will do, we will so 1 minus sin square theta 1 minus sin square 2 half will be basically 1 minus theta 1 square theta 2 square minus theta 1 4 by 3 minus theta 2 4 by 3 half and then it will look like you will see this 1 minus half theta 1 square plus theta 2 square plus theta 1 to the power 4 by 3 plus theta 2 4 by 3 and minus theta 1 square theta 2 square by 4, okay. So, here we are then substituting here, and if you substitute the expression for phi will look like this, okay, approximately. So, it will be half C1 theta 1 square plus C2 theta 2 square minus PL theta 2 square minus theta 1 4 by 12 plus theta 1 square theta 2 square by 2 alpha C1 theta 1 plus C2 theta 2, okay. So, we are assuming that as if alpha 1 plus alpha 2. So, alpha is nothing but alpha 1 is equal to alpha 2 is equal to alpha, okay, that is okay. So then if you differentiate del pi by del theta 1 is equal to 0 and del pi by del theta 2 is equal to 0, that you see 1 theta 1 minus PL theta 1 minus PL theta 1 plus PL 6 theta 1 cube minus theta 1 theta 2 square and alpha C1. So this is equilibrium configuration, okay, by differentiation. So what you see that here, so interesting part is, look, until this it is linear, so you can easily form a eigenvalue problem, right? And this nonlinear term, if you linearize it, means nonlinear term we neglect, right? And neglect imperfection as well, then it will give you what? The eigenvalue problem, and from eigenvalue problem you can find out P critical. So P critical will be, if you can clearly see, P critical will be C1 by L and P critical C2 by L, right? So length L, so P critical one is C1 by L and another P critical 2 is C2 by L, right? From where you are getting it? If you linearize, just consider some linear eigenvalue problem, right? We are linearizing the trigonometric eigenvalue problem to algebraic eigenvalue problem, linearizing we are getting. And then the mode shape you are getting, mode shape will be what? Theta 2 will be plus minus theta 1. That means one mode shape will be 1 1, another mode shape will be 1 minus 1. Those are symmetric, right? Linear. Now if we include nonlinear terms and others, we will do in the next lecture. Thank you very much for today.